Just a reminder, if you haven't been in this room yet today, we're taking questions at the center mic rather than running mics just due to the size of the room. So if you have questions, I'm sure John will be happy to answer them for you if you just line up for the end of the talk. Okay? And so, take us away.
Okay, thank you. So I like to start my talks by asking the audience a question. So here's the question: who really, really loves testing? Okay, maybe half a dozen, or a little bit more. That's not bad. So you're pretty typical as an audience. Testing, it turns out, is not the most popular part of software development. So I just want to start off by thinking about why that is. Why is testing hard? Well, imagine that you're writing a test suite for some code that has n features. What are you going to do? You're going to write maybe 3 or 4 test cases per feature. That's perfectly okay. That's a linear amount of work. But we all know you won't find all the bugs if you do that. Because some bugs only appear when 2 features interact. So what are you going to do? Are you going to write tests for all pairs of features? Well, that's a quadratic amount of work. That doesn't sound so good. And even if you do that, then not all bugs are going to appear if you test for features in pairs. Some bugs only appear when you use 3 features together. And that's a cubic amount of work. And this is now starting to sound really pretty bad. And of course, it goes on from there. But if you consider race conditions as well, so that errors don't even appear every time you run a test, it just gets harder and harder. And in the end, it's hair-tearingly difficult. You can never test enough. So what's the solution? Simple. Don't write tests. Generate them. Because we still want to test our code, right? So I'm going to talk about QuickCheck, a test case generation tool I've been working with for quite a long time now, which originates from a paper by Kuhn, Klassen, and myself. We're up on the top right corner there. And the way that we normally use it is that we start off with some API under test, and then we generate random sequences of calls. And we keep doing that until a test fails. And now, when a test fails, usually this sequence of calls may be quite long, and it's very rare that all the calls in that sequence contribute to the failure. So the next thing we do is try and identify the calls that are responsible and shrink the test case down to a minimal failing example. And that's what we then report to the user for diagnosis. That's a bit abstract, so if you haven't seen it, I'm going to do a demo of QuickCheck now. So I'm going to demo a circular buffer. If I can get the code to appear here. Well, that's not what I wanted. Curses. Okay. So this is a circular buffer in C. Most of you probably write C better than I do, but never mind. So here's a struct to represent the buffer. We've got a pointer to where the data is going to be stored. I'm going to keep track of the next index to put something in, the next index to take something out, the size of the buffer, and so on. Here's the code for creating a new buffer. We have to allocate memory for the data, initialize the fields, allocate memory for the struct, assign that, return a pointer, and so on. Here's how we put something in. We write the argument to the data area at the input pointer, and then we increment the input pointer modulo the size. Very simple. Obviously no bugs, but it's a nice example to test. And here's how we get something out. We read from the data area at the output pointer, and then we increment the output pointer modulo the size. And I've got one more operation here that just tells us how many things are in the buffer. Just take the difference between those indices modulo the size. So that's my code, and I'm going to test it from Erlang. So let me just compile that code. It's in the file q.c. Okay, and now I can call that C code from the Erlang shell. So let me just demo it. I'll create a Q with space for 5 elements. There we are. Let's put 1 into it. Let's put 2 into it. Okay, let's ask how many elements are in the queue at the moment. 2, that's good. Let's take something out. There's the 1. There's the 2. There's uninitialized memory. And some more, and some more. Oh, look, there's the 1 again. There's the 2. It's a circular buffer. So it's C code, and it behaves exactly as C code would expect. So now I can test this code from Erlang, and it's the Erlang version of QuickCheck that I'm going to demo. So what I'm going to do is generate some tests for the C code, which I will do by calling QuickCheck. Oh, wait a moment, let me just compile my test code. And now I will call QuickCheck and give it my specification as an argument. Oh no, a test failed, but you saw everything working. Okay, so what's happening here? What's happening is that we generated a random test case, and what you see up here, this was what happened when I ran the random test, and I think we can agree you probably wouldn't want to debug that. And then QuickCheck has searched for the core of the test case, the minimal example, and down here, this is the part that I want you to read. Okay, this shows us what happened when the test had actually failed. So what happened? I created a queue with space for 1 element, I put a 0 into it, and I asked how many values are in the queue. And size returned 0, but I just put something in. Okay, so I want you to help me now. Here's the source code for size. What's wrong? Okay, so think of the example. I created a queue of size 1. I put 1 thing in. What happened when I did that? Oh, yes, the size is 1. So the size function returns the difference between 2 pointers, modulo 1. But that's always 0. In fact, when I put something in, I incremented the input pointer modulo 1. So that's also 0. So, oh dear, putting something into the queue didn't change it at all. And if you think about it, actually, whenever I make a queue size n and I put n things in, the input pointer is going to wrap around. It's going to look like an empty queue. So I can't distinguish full from empty queues. That's the problem here. So my representation is inadequate. Any suggestions for a fix? What? Well, I am storing the size. I could, for example, store a Boolean to keep track of whether the queue is full or empty, but then I'd get lots of special cases in my code. That would be horrible. So there's a lovely hack, which I'm going to show you. So the problem only arises when the queue is full, right? So here's what I'm going to do. When I'm asked to create a queue of size n, I am actually going to create one of size m plus 1. What does that mean? That means for somebody to observe the bug, they must put m plus 1 things into a queue of size n. And that means it's their fault. And I have successfully avoided blame, which is the goal of all good software engineering. So let me recompile my C code. And then I will just run the last test again. I can do that if I just remove QuickCheck here. So this will run the last failed example. Now it passes. And now I'll run random tests, and let's see what happens. Oh, it still didn't work. There must be another bug. Okay, so look what happened here. I created a queue of size 1. That's really 2. I put something into it. That was okay. I removed the thing by calling get, so now it's empty again. I put something else into it. That's okay. How many things are in the queue now? I put 2 things in. I took 1 thing out. 1. And so size returns -1. Oh no. What happened here? Well, if we go back to the code for size, right, what happened was I put two things in. The Q is really of size 2. So the input pointer has been incremented twice, modulo 2. It's wrapped right back down to 0. The output pointer, I've taken one thing out, it's been incremented once. So here, I'm computing 0 minus 1, that's minus 1, modulo 2. What is minus 1 modulo 2? I've studied mathematics. I know what it is. It's plus 1, right? Let's just check with Erlang. Minus 1 modulo 2. Oh no! Erlang doesn't implement modular arithmetic properly. It returns minus 1, and so does C. So that's the problem, right? I thought modulo would always return something positive, but if this expression is negative, I get a negative result from size, and that's clearly wrong. So I've got to make sure this expression is never negative. How can I do that? Yeah, thank you. Absolute value. Okay, let's just make sure that works. I'll recompile the C, rerun the last test. It's fine. So where am I now? I found a problem in my code. I created a test case that provoked it. I've fixed my code. I've rerun my tests. All my tests are green. I'm done, right? Would you like me to run some more random ones? Just so we feel comfortable. All right, let's see what happens. Oh no! It still doesn't work. What's happened here? Okay, now I made a Q of size 2. That's progress. That means Qs of size 1 work now. We know that because it's minimal. Okay, so what does this test case do? It puts 3 things into the Q. It's really size 3. And I take one thing out. So how many things should be in the Q? 2. What does size return? 1. Why is that? Because the input pointer has wrapped around again. So this is 0. I've taken one thing out. This is minus 1. Modulo 3, that should be 2, mathematically. But if I take the absolute value, I get 1. So what I need to do is not take absolute value. That's an easy mistake to make. I have to make sure this is positive in some other way. And I can do it by adding Q size here. And that will ensure that that is never negative and everything should work. Let's see, I'll recompile the C, rerun the last test. That passes. Should I run random ones? Just to be on the safe side? Maybe. Yes, 100 tests passed. 200, 300, 400, 500. Seems to be working now. Okay, well, thank you very much for helping me with my debugging. Let me go back to the slides here. So what we've seen here is that with the random tests and the properties, I haven't shown you the test code, but my test code was able to find a variety of different bugs with the same test code. That's really nice, isn't it? And what you've seen also is that when a bug was found, then it was shrunk down to a minimal failing test case. And I hope you'll agree with me that those minimal tests are quite easy to debug. It's great to know that everything that appears in a test case is relevant to the failure. That's an enormous help for debugging. If you look at the first randomly generated tests, they contain a lot of random rubbish. Think of it as noise. Why? It's their purpose. Random rubbish is very good for provoking failures, but it's very bad for debugging them. So this shrinking process that simplifies the test case as much as possible, we think of as like extracting the signal from the noise. And I think it's a key technique for making this approach useful. Okay, so I've shown you testing a very tiny piece of C code. I didn't show you my test code. It's actually as large as the C. And if that were true for larger pieces of software, then the whole approach wouldn't be very useful. So you might be wondering, does this really scale? So let me tell you about the largest project that we've used QuickCheck to test. And that is part of the AutoSAR basic software. There's a diagram of it here. I'm not going to explain this in detail. What is it, though? This is the structure of software that runs on every processor in a car that follows AUTOSAR. So you can see here, there are a lot of colored boxes. Each colored box is a module, and then the boxes that contain colored boxes are subsystems. So you can see there's an Ethernet stack on the right there. The second thing is a CAN bus stack. The CAN bus is a network that's very commonly used in cars. Most of the communication goes over a CAN bus. And then the other stuff does routing, there are some other protocols and so on. The point is just that there's quite a lot of software in the AUTOSAR basic stuff. And there is a standard that specifies how this should behave. Why? Because car manufacturers, like Volvo Cars, want to be able to put subsystems together containing code from different providers. Now, you might think that the right thing to do would be to have one implementation of an Ethernet stack, for example, that everybody just shares in the car industry. One open source solution would ensure that all the different components work together. But that's not what they've done. What they've done instead is they've standardized how these components should behave so that there are many different suppliers of CAN bus stacks. And so you can be running a CAN bus stack from one supplier, in your gearbox, and from a different supplier in your engine controller, and they have to talk to each other. And thanks to the standard, then everything should just work. Well, guess what? It doesn't. And in fact, when you first put a car together, you can't even boot it, let alone drive it. And a part of the problem can be that the suppliers of this basic software didn't follow the standard, and so their components don't work together. So Volvo Cars paid us to develop QuickCheck models of all the AUTOSAR basic components and to test the software from their suppliers to see if they were following the standard or not. And I can show you one of the bugs that we found. Here it is. This is in the CAN bus stack. So the CAN bus can carry one message at a time, and all the messages on the CAN bus have an identifier which also serves as their priority. So this test case, first of all, sends a message with priority 1. And what happens? Well, we can observe that it sends message 1. So now the bus is busy. Then it sends 2 more messages with priority 2 and 3. Okay, so now you can imagine that the client software has called the CAN bus stack saying send these messages, but of course it can't send them yet because the bus is busy. So they get queued up. Then the test case calls transmit confirm. So sending a message is normally called from above the protocol stack. Transmission confirmation is called from below by the hardware bus driver. And in this case, it's confirming that the message with identifier 1 has been sent. So now the stack has 2 messages queued up, and it must choose between them. And the trick about these priorities is that the smaller the number, the higher the priority. So which message should be sent next? The one with priority 2. And which one was sent? The one with priority 3. So that was kind of interesting. And in this case, we actually had the source code of the CAN stack. Often we don't have source code of software we test, but in this case we did. So we could look at it, we could find out what the problem was. So I can explain it to you. In the CAN bus, the message identifier serves also as the message type. And in the first version of the CAN bus protocol, there were 11 bits allocated for storing the message type. But if you think about it, that's like saying you can have 2,000 different types of message in the entire car. It's like saying your Java program can only have 2,000 different classes. It's just not enough anymore. So as a result, the CAN standard has been extended, so you can now use an extended CAN ID of 29 bits. And that allows, well, enough different message types, even for today's software. But you can still use the old format. So when you send a message, you have to remember, what kind of identifier have I got? Should I use the small format or the large one? And it's the numerical value that determines the priority. In this particular CAN stack, then this identifier was stored in an unsigned 32-bit integer, And look, the extended field is only 29 bits long, so you've got 3 spare bits. And the top bit was used to record whether the message should be sent with an extended ID or a standard ID. So guess what? What I didn't show you before is that the message with priority 2 was encoded using an extended CAN ID, and the C code that was deciding which message to send, okay, the developer forgot to mask off that top bit before comparing the priorities. So it was treating the message with priority 2 as priority 2 to the 31 plus 2. And that's why it was sent second and not first. So I really like this example, partly because it's a very low-level bug. A C programmer forgot to mask off a bit in this protocol stack. But even so, you can provoke the bug with a short sequence of API calls. And you can find that short sequence by generating longer random ones and shrinking them, as QuickCheck does. So it's a very nice illustration of the technique working at a much larger scale. Also, it's an important bug. The CAN bus has priorities for a reason. Everything in a car pretty much talks on the CAN bus. The stereo, the brakes. So here's a tip. Next time you're emergency braking, don't fiddle with the volume on the stereo. So in this project, we read 3,000 pages of PDFs containing the specifications of all of these out-of-cell components. We turned that into 20,000 lines of QuickCheck code, which I think is quite a good ratio. We only needed 6 lines of code to test what 1 page of PDF said. We used that to test in total about 1 million lines of C code from 6 different suppliers. And even though when we got the code it was supposed to be working already, we found more than 200 problems, of which more than 100 problems were in the standard itself. I found one of those myself where, first of all, there was a requirement in the standard, very clearly stated, and then afterwards there was a paragraph explaining what it meant that contradicted what the requirement said. So, you know, what are people to do? The other thing we found was that in those cases where we could compare our test code to existing test code, ours was 9 times shorter, and moreover, tested more. So, does this technique scale? Yes, it scales. I also want to show you, I can't resist showing you my favorite ever bug. This is a bug in the database that comes along with Erlang. And to provoke it, here's what you have to do. First of all, you have to open a table. And then you have to close it and open it again. No, really. After that, you do 3 things in parallel. 1 lookup and 2 insertions. And about every 100th time you execute that, you crash the whole database. So the database concerned, it was crashing in production at one of the biggest users in Sweden about once a month. And I knew about this bug, and I thought it would be really fun to hunt it down, so that's why I went looking for it. But by the time I found this, then the guy who was maintaining the code had spent more than 6 weeks working at the customer, trying to figure out what on earth the problem was. And at the end of that time, their best guess was, it seems to happen when the file is about 1 gigabyte. Maybe it's something to do with rehashing. Now we know you need a database with at most 1 record and only 5 or 6 function calls to reproduce the problem. And once I'd found this very small test case, that I sent it to the maintainer, and next day he sent me a fixed version. And this bug really shows the enormous value of shrinking and getting a small test case out. What a dramatic difference it makes in how easy it is to debug these problems. The other thing I really like about this bug is that there's no way anybody would write this test in a test suite. Right? I mean, there's quite a few calls in the API. Why would you test this particular one? And yet, this is the smallest example that can provoke this bug. So it's a kind of bug that you can really only find by searching for them. Okay. I just want to go back now to one of the counterexamples I showed you. Remember this one? So this is of length 5, okay? It's 5 steps. And so you might think, if you're searching for a small example like this, maybe you should be running tests of length 5. But that isn't what we do. I measured the lengths of tests I was running, and here's the graph that shows what I was doing when I was running that demo for you. So you can see that the test cases I ran varied widely in length. About 8% of them were length 0, which might seem a bit excessive, but it's not so serious. Those tests run very fast. But then there were much longer tests. The longest ones were more than 200 steps. So why do we do this? Why do we run much longer tests than the counterexamples we're looking for? In fact, the average here is over 15 steps, so over 3 times the length of the counterexample that I actually wanted to find. So the key thing here is to ask ourselves, well, how quickly can we actually find faults by running these random examples? How does the length of a test affect the probability of hitting a fault? So I measured that too. So look at this. This is the probability of a test case failing on the y-axis, and on the x-axis it's the number of steps in the test case. And because there aren't so many test cases of greater length, it gets a bit noisy towards the right. But nevertheless, when you look at it, you can see, well, actually, all the tests of length up to 5 passed. So I didn't manage to hit this bad case in a random test of length 5. But then, as the tests got longer and longer, so they got more likely to fail. Well, now you might say, of course, a longer test case is more likely to fail. It's doing more stuff, so there's more chance it'll do something wrong. And, of course, that's true. So this graph isn't really the one that you want to see. What you want to see is, as I do more work running a test, how does the probability of failure per unit of work change? So what you want to see is this graph divided by the length of the test, right? Because each call is on the assumption they cost about the same. And this is what that graph looks like. Okay, so this is the probability of one command failing in a test case of varying length. And you can see that for the shortest tests, well, there's simply no point running them. They all pass, because the shortest failure was 5 steps long. But after that, tests that are only a little more than 5 steps, they most likely will pass. But once we get up to the 20 to 40 commands range, that's where we're maximizing the probability of each command revealing a failure. And this is something that we have observed again and again and again in many different contexts, that generating longer random tests and shrinking them back down is by far the fastest way of finding short failing examples. So why is that? Well, I can give you some intuition. I'm waving my hands here, I admit it, but there's some truth in what I say anyway. So this represents a long test case. Suppose it fails. Well, as I showed you, when a test case fails, it's usually because of some subsequence of commands. Maybe these 5 commands were responsible for failure. So what about all of the rest of them? Well, it turns out that quite often the other commands in a test case don't matter. In other words, as long as these 5 commands appear somewhere in the test case, it's quite likely to fail with the bug that we're looking for. So now ask yourself, in a long test case of length n, how many ways are there of embedding 5 steps into that sequence? It's exponentially many, right? You're getting exponential benefit for a linear amount of work. Is that good or what? So that explains why really this kind of testing is unreasonably effective. And it's quite amazing to see. Okay, well, if you want to know more, Haskell QuickCheck was the original version of QuickCheck. There's a paper from 2000 that describes that. Quviq QuickCheck is the one that I demoed today, and we have a company that supplies that along with services. But there are also many, many other tools that have been inspired by QuickCheck, like test.check enclosure, Scala check, fscheck in F#, and so on. So I encourage you to go and look at some of these tools and try them out. And if you haven't done so yet, then you will be amazed. Don't write tests, generate them.
So we have some time for questions. If you could just use the center mic there next to you. Yeah.
Ryan Newton from Indiana. Hi, John.
Hi.
So aside from the takeaway that I should not get in a car, one of the things I was wondering about your talk is about shrinking test cases in the context of non-deterministic failures, like the database one that you demoed. Because at that point, each shrink step may or may not yield there's no true question of whether or not the shrink succeeded or not. Do you simply set a threshold for how many times you try it each time you shrink?
Right, so suppose you're trying to debug a non-deterministic failure and you've got a complex case that fails and you're doing it manually. What will you do? You'll try to simplify it, but you won't run that test just once to see if the failure is still there. You have to run it repeatedly. That's what we do. We just automate it. And how many times you run a test before you decide that this one doesn't fail, that depends on how rare the race condition is that you're looking for. And that's something typically that the QuickCheck user will adjust. So for the database examples, to get reliable shrinking, I ran each test 1,000 times.
Okay, thanks.
It can be a little slow, but it's a whole lot faster than trying to figure out what's going on without doing that.
Thanks. So what happens when you use QuickCheck within a first or second year programming course?
I have used it on the very first programming course, and I taught the students a method for writing functions where they wrote down the type, they wrote down the names of the parameters, and I got them to write down a property before writing the code. And that was reasonably okay. The students did what I told them. They wrote a lot of properties, they got a lot of benefit. But I think that was perhaps the wrong place to do it, because at that time it was not easier for the students to write a property than it was to write a simple function. So I think it makes more sense to introduce QuickCheck testing once students are writing code that's a little bit more complex, so that their properties can be much simpler than the code that they're testing.
Hi, thank you very much for creating QuickCheck. I am a little curious if you have any recommendations about how to use it to explore like very large state spaces. And in particular, I noticed in the Quviq QuickCheck, it seemed that perhaps you start with really small ones and iteratively move to bigger cases. Basically, I found it difficult to generate good examples when I'm dealing with large, like very high dimensional data structures.
Yes, so I think random search is very good at exploring very large spaces, because what other approach can you possibly take? If the space is very large, you can only sample from it, and random sampling is quite effective. But what I don't have time to get into in this kind of talk is to discuss the measurement of test cases. So one of the downsides of using a tool like QuickCheck is you don't see the tests. And as a result, when you're generating complex tests, it might be that almost all of them are rather trivial. So you might get a false sense of security. So it's very important that you collect statistics about what the tests are actually doing. Look, for example, how well am I covering my source code? If you're missing part of it entirely, you need to adjust the distribution. We measure all kinds of things. So for example, I often use a test of a process registry that maintains a table of process identifiers. And the most simple way of generating those tests generates a table that is almost always empty. Right? And I know, I measure the size of the table, and I adjust the distribution so that I get a nice spread of sizes. So using a tool like this doesn't free you from needing to think about what you want to test, but it raises the level at which you think about that. You need to think about, what should I measure to have confidence in my tests? And then, once you've measured it, how should I adjust the distribution so that I get the measurements that I want? So there's a lot of skill and experience in doing that, which I don't have time to discuss in a talk this length.
Thanks.
Hi. So I was wondering in particular, it sounds like at a high level, the goal of a tool like QuickCheck in some sense is to find counterexamples to some theorem. So you state some property of the program and you're looking for a witness that that theorem is false. So I was wondering in particular if you had considered, I don't have a great sense of sort of the overlap between this and the formal methods literature, but if there are techniques from, say, SMT solving that could be useful here or vice versa.
Yes, so that's right. So what we do is we formulate a property of our code, a correctness condition, and then we look for a counterexample that shows that it's not correct. Quite often what we discover is that the property is not correct. Right, so in general, what happens is that, funnily enough, customers write their code before asking us to help them test it. And that means that in practice, you usually test some code that has already been tested to a certain extent and that works to a certain extent, which means your test code is the new code. So your formal specification is the new code. Of course, that's where the first bugs are. So one of the nice things about using a tool like QuickCheck is that there's very little manual effort involved in discovering a discrepancy between the specification and the implementation. And then you can quickly see, okay, here's a counterexample. Then you have to ask yourself, is it a real counterexample? Is it a bug in the code? Or is it a misunderstanding of my spec? And you usually go through a process of refining the spec until you actually have captured the intention. And from that point on, the bugs that you find are in the implementation. So if you try to start off with your spec and assume that it's right, and then try and prove that the implementation meets it, then you're going to be doing a lot of proof work that may end up being wasted because the specification was wrong in the first place. So I see using a tool like QuickCheck as an appropriate step you would take before putting in the effort of trying to do a formal proof. Because I think you get a lot of the silly mistakes in the spec out of the way, and many of the silly mistakes in the code out of the way, so you can start trying to prove that your implementation is correct in a good position where it most likely is correct.
Hey, John. Nice talk. So I guess one of the interesting things from my perspective, you're working with Haskell in particular, and it doesn't provide a first-class support for expressing the kind of properties that you want to look for. But there are programming languages which actually do provide support for expressing, pre and post conditions and other properties that you want to check. And I'm wondering, what you think about languages like that as they would help tools like QuickCheck, because those things would be written into the code maybe from the beginning, hopefully.
Okay. So the demo that I ran was actually with the Erlang version of QuickCheck.
Sorry, yes, yeah.
And I didn't show you the test code, but what it consists of is a state machine model of this circular buffer, including preconditions and postconditions and state transition functions and so on. So that we've built a framework for expressing specifications in that form. Because when we started the company, we discovered our customers didn't have all that much purely functional code. And the customer is always right. So we worked on the state machine modeling formalism. So I think you're perhaps referring to languages like Eiffel that have contracts built in.
Eiffel would be a good example, yeah.
Yeah. So that can, of course, be helpful. If an assertion fails in code under test, then that tells you the test has failed. But in QuickCheck, we use these state machine models not only for deciding whether a test has passed or failed, but also for generating tests. And so that means that we need to use these preconditions in particular in a slightly different way. If they were hidden from us by being written in the code of the system under test, it would be harder to use them for test case generation.
But you could extract the preconditions, right? I mean, that's what I'm imagining.
Yeah, possibly. One of the things that has worked well for us is that QuickCheck, the version of QuickCheck that we use, is entirely black box. And that means that we can test code in Java or C++ or whatever. The very first customer we had, we managed to crash a base station which we knew was programmed in C++ generated from rows RT. And the most serious crash we found, we looked in the log, and it was full of Java exceptions. I thought, what? Where did they come from? So it turned out that we had corrupted the state of the base station and violated a fundamental invariant. But the base station also had an operator's GUI. That was in Java. And that GUI was the first thing to fall over when the state of the base station was corrupt. And so that's how come they appeared there. And we could do that because the testing is black box. All we have to do is invoke the system under test using the same test interfaces that anybody else would use for testing it. And that limits what we can do. We can't process the source code, but at the same time, it gives us a great deal of freedom in the kinds of systems that we can test.
Thanks.
Okay, let's thank the speaker again.
Thank you.
Okay, and so now there's a coffee break, so we'll see you in a little bit.